of my co-author. So this is the work that we done in collaboration with the Mitsubishi Electric Research and Development, a group that appears to be located very near this place. This is about railways and automated trains and in particular the railway networks. So let me explain a bit this context. So in particular in the design of automated trains, there are a representation of the railway network where your trains are running. And so this is more or less a standardized representation of railway networks using databases. So here is a very simple example. So roughly speaking, the railways are made of segments of rails, and segments are connected together. So let's see, for example, the segment 2 here in the database has a prev 1, a next 1, and next 2 fields that so seg 1 is the predecessor, and seg 3 and seg 6 are next segments. So this roughly shows you how the connections are described. And you have also switches in the network. So typically the switches will connect 3 segments together. So the tip segment here for switch A, seg 2, and the right and left branches, seg 3 and seg 6. So given this kind of description of a railway network, the question we were asked from Mitsubishi Electric is to check that a given network is satisfying some properties, some structural properties. So the kind of properties that are expected to hold in order for the software in the automated trains to work properly. So this kind of, I'm going to call them invariants, it's a property that should hold for the network, could be very simple like this one. The length of each segment is within some bounds, so segments have some length, but some properties are quite complex, so involving the topology of the network. So here it's not so easy to understand first that it should not be possible to go from the left to the right part of a switch without passing the tip. So let me maybe explain on the picture. The switch C here is not satisfying the property because you can go from the right to the left without passing the tip. Okay, so this is a kind of properties that we should check that in fact are not occurring in the network. So we were asked from our collaborators from Mitsubishi to find a way to checking this invariant, and with maybe 2 main goals in mind. It should be efficient, but it should be come with a high level of guarantee. So that's where we wanted to work on. In my group, we are not very familiar with Dafny', but more with Y3. So we think that it's a perfect application for Y3, but it will be the same, of course, for Dafny'. Use this kind of environment to design a checker for this kind of constraint, prove it correct, and also run it efficiently. So this is the. So in fact, in particular, let me give you detail. When you define a code like this in Y3, you can compile, execute it by extracting first to OCaml and compile it regularly. So that's the main idea of the tool that we designed. We want to write a tool that will read the database with this CSV file that you have seen before, and we have to write the constraint in some language, some formal language like this one, expressing the simple properties on the length of the segment here. Okay. So we have this picture for describing this little prototype tool. So the central part is designed within Y3, but we have a front end where we do the concrete parsing of files that is done outside the Y3, but it's written in OCaml, and it's perfectly possible to link the verified code and the unverified code. And we get an answer at the end if the constraint is valid, or in fact we want also to have counterexample when it's not valid. But internally, all this is designed within Y3 and proved correct. There is some part of checking properties of database, but the main part is here, the checker. And I'm not going to talk about it, but there is also a question of optimizing the constraint given by the user. So we have to decide what would be the language. So we started from a classical, let's say, first order language, but it's not classical first order because the quantification, in fact, happens on typically a set of segments. So it's in fact a bounded quantification, and the set here is a finite set. And we have in particular some operation of sets, so union or membership, but also the describing set by comprehension, which is important to have for describing the constraint. So what did we do with that? So we define this language within Y3, so it's very easy because we have the way to define algebraic data types within the language. And naturally, we want to define its semantics. So on paper, you will write some inductive rules to define the semantics. And you can map this into inductive definition within Y3. So it's not very readable. You cannot really read here, but it really corresponds to what you would write on paper. So I pretend that this is quite close to what you wrote on paper. So given this semantics, which is quite long to describe because, so sorry, this is an example of the semantics related more to the database, accessing a field in the database. So there are quite a lot of premises to check if the field name is really in the database and so on. But it's quite mathematical and there is no real difficulty. So after this semantics is written, we want to write a code that will check a formula against a database. So it has this prototype, let's say, taking database, local environment because we have local variables, and an expression, and essentially it will return the value of that expression. So this is the specification. So there is a normal exit. So when we want to prove that if it returns a value, it satisfies the semantics that we formalized before. And there are a bunch of exceptional cases because we have to take into account the fact that some data may be not well written, such as a field that does not exist in the database. So given this, so I don't show the code, of course, but there is a code that has some in fact, I have the number of lines. Thank you. So it's roughly the numbers we have for the predicate is 150. The code itself for the program is 250 lines. Let me mention maybe because we have operation on finite set, we are using set of iterators, which are a kind of higher order construct in Y3 that is very nice to use. There are, so the number of VCs here, 182. And yeah, you have some other code when you load the database, but at the end, if you write all this, you can discharge all the VCs with the SMT solver that we have typically in the portfolio in Y3 in fractions of seconds. There is no difficult proof obligation here. So this is the core of the solver, but there is the question about the topology of the network that requires some more complex things. So I'm going to let Noé to explain a little bit what happened with the reachability.
In addition to what Claude just presented, we have some predefined function in which we'll add some arithmetic function, add multiplication, some set operations such as the membership and union. And we also have a way to check the reachability from one segment to another, avoiding a certain set. To achieve that, what we wanted to do is to take a generic model, any kind of algorithm that do reachability in directed graph, and to implement it in YML, and to prove it that it could work. And what we decided was a depth first search, and we also needed an encoding for our real network, because it's not as simple as one could think. We need the encoding, because if we want to reach, if we say we want to reach from seg1, seg7, if we just take it as face value, you could say you could do seg1, seg2, seg7. But we're using some train, so once the train goes one direction, you cannot go backward into seg7. But even with the constraint of going always forward, you will go seg1, seg2, seg3, seg6, seg5, seg4, but when you return it, the problem we have is any kind of algorithm that do reachability cannot visit a node twice. So once the seg3 has been visited, when we go back, we cannot visit seg3 again, so we couldn't reach seg7. Our solution to solve this is to duplicate all the segment into two nodes. One node next and one node prev, if you remember the definition we had in the CSV. And so here, if we say we start from seg1, you can clearly see once you go into seg2, there's no way to go to seg7. And when you go through the loop, seg1, seg2, seg3, seg6, 5, 4, you go into the prev, you go back to seg3 prev and not the next. So for the algorithm, it doesn't know that this is the same segment, so it will be able to go through this one and find that there's a path to go to seg7. The semantic we have, our specification, when we ask our solver, does it exist a path avoiding in our graph from one source to a target and avoiding a set A? This function will ensure that the result we have expect that there's a path where we have the definition of path avoiding for graph, source, target, a path, and an avoid. The definition we have of our path avoiding is an inductive one, where the empty set, the empty path, is a vertex to is a path of a vertex to itself, where we just need to ensure that V is part of our graph and V is not part of the set we want to avoid. And for any non-empty path, how do we do it is, if we want to reach from V0, V2, what we need to ensure what we require is just that V0 is not part of the empty set, that there's a path avoiding from V1 to V2, and that V1 is a successor of V0. And in addition, you'll see here that we added V0 in our avoid set to expulse any kind of cycle in our path. Because, yeah. To be able to prove that, our generic model needed 59 VC. To encode the real network, which was a bit more difficult because we needed to take the data, our database, and translate it into vertex. And for each next and for each prev, we needed to have its own function. So there's a lot of VC, but it's mostly just duplicate that we couldn't avoid. And to be able to call our generic model of exist path avoiding, we need to make sure there was some requirement. We need to make sure the requirements are correct. And to do that, in order to do that, we needed 35 VC. Everything was proven with the four classic provers, but it was a bit more difficult than for the prover than the other module, since some VC needed up to 4 seconds to be proven, which is quite a lot in this kind of things.
Okay, thank you. So to conclude, we were able to build an operational prototype for maybe somewhat a simple language, but it's working, it's proved, and it's efficient. So I didn't show there the benchmark that we did. We had some comparison. So please look at the paper that we linked in the program. So we didn't talk about the type checking errors. So this was one requirement given by Mitsubishi Electric, is that if the user is not able to write a well-formed constraint, there should be a nice feedback. So we have that also, but it's not a proof part of the prototype. And so it's important to have also this reporting a counterexample, but okay, see the paper. And we have, in fact, currently a work about optimizing constraints before executing them. So it's important to modify or compile a little bit the constraint before executing them. And in fact, you have ongoing improvement on that, not yet finished. And and maybe let me tell you that the comparison with the tool Ovado is very good for us. We are in fact more efficient than this other tool. Thank you very much.
I have a quick question about the efficiency. So you're doing a depth first search without any dynamic programming kind of structures that would accelerate the search. It's surprising that you're always better than Ovado because they're not doing this, or?
I don't know if you want to answer. It's maybe a bit technical. No. So it's depth first search where we record the visited node, and I'm pretty sure that it's mostly quasi-linear algorithm. Okay, so regarding efficiency, we are search. Regarding Ovado, it's not so easy to compare because with Ovado you have to write a constant, as far as I understand, in a language that is close to the B formalism, and this kind of thing, which is a recursive thing, is quite complex to write using fixed point construction. So it's not a very good. I mean, for the problem is you're not executing the same thing at all. In fact, so the problem is more that it's more difficult to write reachability predicate with this tool.
Is there a last question?
Actually, I had the same question about reachability. Since you have that, like you need to double the graph to apply this algorithm. So like, I think there might be another algorithm on the original graph that maybe it's more complex. Because I was surprised when you said, okay, we need to double it.
In fact, we really wanted to use a directed graph algorithm from the shelf, right? Okay, yeah, and if we could, in fact, write an ad hoc algorithm for railway network, but it was not very satisfactory. We would like to reuse.
Yeah, but if it's more, if it would be more efficient, then maybe.
No, I don't think it would be.
Be more efficient, because if the ad hoc solution will have add a lot more step than just doubling the number of segment doesn't cost that much in reality, because yeah, it won't cost much.
Of course, you use more memory somehow.
Yeah.
But regarding the time consumption, I'm thinking it's the same.
Is there like, I mean, I don't know if maybe it's like informal argument that it's basically the same graph. Like it's maybe obvious, but maybe it's good to have a proof that, I don't know, that when you double, it's basically the properties are the same. Like
I'm not sure I completely remember here, but we have a specification of what is reachability in the network, and we prove that it's the same as the reachability in the encoded graph. I think we have that, but I'm not sure.
Yes, we have that in the encoding
to justify that this is a correct encoding.
That's the main cost of VC is to specify that the segment we have in our database is exactly the same in our vertex in our normal graph.
And with that, let's thank the speakers.